So really quick check. How many of you have heard of Heartbleed? How many of you have heard of Log4Shell? How many of you know there's a new OpenSSL vulnerability that hasn't been named that's running through the world like crazy right now? Pay more attention. You catch up. So how many of you have had the misfortune of either being involved in these remediations or know some of the other poor souls who had to figure out all the places that you're using them? It's a miserable experience. I don't recommend it. And this has led to a huge amount of focus on what's being referred to as supply chain security, which is not what's insecure about your code, it's what's insecure about all the other codes you consume from the world. So quick check. Is there anybody here who writes code that does not depend on anything from third parties at all? Always curious. Okay, good. Right audience. So this basically begs a very simple question, right? Supply chain vulnerabilities. What is baked into the pie? And this turns out to be a ridiculously hard question for which we have currently an absolutely terrible answer, which is we have a bunch of scanners that go and scan the resulting binaries or containers or whatever and try and tell you what is in them. So I've got a quick question for all of you here. What kind of pie is that? Is it an apple pie? Is it a peach pie? It's very hard to tell from the outside. And this is the same problem we have with scanners. Scanners give you a huge number of false positives, and as far as I can tell, the number of false positives is increasing, which requires a huge expense and investigation to figure out if you have those things in you, to figure out if you have certain vulnerabilities. But they also have a large number of false negatives, so you spend a lot of money to not improve the security of your code, and you still ship vulnerabilities. Sad panda. But there's another way of doing this, because there is one player in the ecosystem that actually does know what goes into the pie: the build tools. So the entity in the world that knows what goes into your .o files is your compiler. The entity that knows what gets linked into your executables is your linker. And so that is a good place to start. Happy pandas. So conceptually, if you're looking for vulnerabilities, what you want to conceptualize the world in terms of is artifact dependency graphs. So at the very base level, we have source code. Just to use C as an example, it's absolutely not the only one we're interested in here. You have C files and H files that get compiled into object files that get linked into executables. And if you're most non-trivial programs, you also have an artifact dependency graph for a bunch of shared objects that you get linked with at runtime for your running executable. Almost every piece of almost all vulnerabilities are going to be rooted at some point down in that source code. There'll be some C file or H file that has some function that is vulnerable. So if we know all the source code files that come up all the way through the artifact dependency graph at the top, we can actually use this to track down vulnerabilities and a bunch of other interesting things. And so what we advocate for with Gitbom, which Bharathi will be telling you more about, is generalizing a bit. So take the specific example I gave in C compilation and generalize it to a generalized artifact dependency graph, where I could have Go source code files coming up, or Rust, or C coming up through Python into containers. All of these things form artifacts in the artifact dependency graph. And if you can reason about the entire graph all the way down to the source code, you can know things in a machine understandable way about your potential vulnerabilities, and also a whole lot of other things. So we made a very fundamental observation with Gitbom. So how many of you use a source code management system that is not Git? Okay, we do have a smattering, and you always have a smattering. How many of you use Git? The vast majority of source code in the world has already been identified and indexed with a Git object ID. Every blob in your repos has a Git object ID. And so we advocate for using those as the generic identifiers for artifacts all the way up the tree, and then constructing documents that describe the relationship in a very formulaic way so they're built deterministically. So if I just have leaf artifacts, like artifact 4 and 5 in this diagram, if I'm describing the inputs to artifact 2, I simply have a file that says blob, the gitoid for artifact 4, and blob, the gitoid for artifact 5, new line delimited in a file, lexically ordered. We all agree on what we're talking about. We'll get the same answer every time. And in the case that I have something like artifact 1 that has dependencies on things that have dependencies, you add to the end of that line something that has the bomb and then the git object identifier of the gitbom document for, say, artifact 2. So you form a Merkle tree. How many of you are familiar with Merkle trees? Very simple. This is how Git stores things. It's a hash of hashes down through the tree, and it gives you the characteristic we love about Git that you can't forge commits. And then once we've built this artifact dependency graph, you can have any kind of metadata that you want referring into it. If I want to build a software bill of materials or an SBOM, we already have things coming into those standards that will let them point to the artifact dependency graph. If I want to keep any other kind of interesting metadata that I may have about this, passing static analysis tests, having been through particular kinds of CI, I want to attest who built it, I can reference the artifacts in the artifact dependency graph by their Git object IDs, and I have a tie between the world of metadata that describes things and the world of the sparse tree of artifacts that we have now with absolute precision. So I'm going to hand it over to Bharathi because what she has done is actually implement this into working things in LLVM so that this can become something that you can generate on demand and transparently.
Okay, thanks, Ed. So why llvm-gitbom? As Ed mentioned, build tools are very crucial for computing gitbom information because they precisely know what goes into an artifact and they can provide the dependency information that is critical for implementing gitbom. Also, it's relatively more easier to embed the gitbom information within the artifact itself while it's being built than after the artifact is built. So llvm-gitbom is an implementation of gitbom in the LLVM compiler infrastructure. So if you look at the tooling for gitbom, they can be classified into two buckets. A set of producer tools, llvm-gitbom is one of them. And these tools produce gitbom data which can be consumed by tools downstream for solving specific problems. And these tools are common, so all of the languages and tools that produce the problem space on the left, they can consume these applications that solve specific problems. So the prototype for llvm-gitbom is based on version 14, and in the Clang compiler, we have implemented an option frecordgitbom, which optionally takes the location of a directory where you want to store the gitbom documents, and also it can be enabled by just simply setting an environment variable, so you don't have to change any of the makefiles. Similarly, for the linker, there is an option --gitbom, and it can also be enabled by just simply setting the environment variable. Currently, we support C language and ELF file formats only. So the bulk of the work is actually done in the Clang frontend itself, which generates the gitbom document and just passes the gitoid or the final hash to the middle end to be embedded into the object file or the executable. So there are two places where you can find the gitbom information. So one is the gitbom document, which is located in the directory that you specify in the option or in the current directory, in the same directory where the object file is located. The gitbom document describes the immediate children of the artifact in the artifact dependency graph. And a leaf artifact is described by the keyword blob followed by the artifact ID of the child. And a non-leaf node or the child artifact is represented by blob, the keyword blob followed by the artifact ID of the child. And then the keyword bom followed by the identifier of the child artifact. So the gitbom of the child artifact is going to tell you how that child artifact itself is built. So how is this all computed? So we basically collect all the dependencies like the header files and C files during a compilation step, the object files, shared objects, linker script, the dependencies that for the linking step, and we record the gitoid or the hash of these dependencies and sort them in lexicographic order. So this forms the contents of the gitbom document. Now you compute the hash of this document, and the name of the document is the same as the hash of its contents. And currently, the two hash types that are supported are SHA-1 and SHA-256. This is because Git supports these two hash types today. So this is an example of the gitbom document. The first one has only leaf artifacts. The second one has a child artifact and the BOM ID of the child artifact. So if you want to see how the artifact 632f ... is built, you can go to the file in 2a/5eb6a ... So that will give you the information about how the child artifact itself was built. And next is we embed this gitoid, the hash of the contents of the gitbom document or the gitbom document that's generated into the artifact itself in a note.gitbom section. So since this has this flag alloc, it parses all the way into the core file as well. And again, we support the dual hash modes SHA-1 and SHA-256. So there is one note entry for each hash type. A note entry has 5 fields, actually. So the type of the note section is nt_gitbom. The owner of the section is the keyword gitbom. What it contains is the gitoid. And what is the length of the gitoid? It's 20 bytes for SHA-1, and it's 32 bytes for SHA-256. So LLVM readelf can be used to read the contents of this gitbom document using the option N. So it understands how to read this newly created note section. So what is the increase or the difference in size by adding this section? So the expected change in the binary size is we have a total of 52 bytes for both accounting the two hash types. And then every note header takes 20 bytes, so that adds another 40 bytes. So 92 bytes for the node.gitbom section, the contents of this section. And because you're adding a new header, you're going to add another 32 bytes to the section header. Plus, because you're inserting a new section, there can be some padding adjustments and differences in layout that can, plus or minus the size. But in practice, what we have seen is this section fits nicely into the memory that's already allocated for padding, so you don't incur that much of a difference in size. And we have benchmarked llvm-gitbom with OpenSSL and Linux kernel builds, and the overheads we've seen are very low. For OpenSSL, we built the latest version with a parallel build, and the increase in the build time was about 6%, but in practice, this was less than 3 seconds. We built OpenSSL, and we compared the build directories with gitbom enabled build, and with gitbom enabled and without the gitbom enabled option. And the difference in the size of the build directory was only about 650 KB compared to a baseline build directory size of 332 meg. And the addition of this new section itself increased the size of this library by a very negligible amount. So it's, again, 0.01% for 0.001% for libcrypto and 0.03% for libSSL. The number of gitbom documents, so we generate one gitbom document for every object file and every library or executable that's built. So there are about 3,150 gitbom documents that take up a size of 29 meg, but it compresses well to under 2 meg. And typically, you don't have to enable this option in developer mode. It's only for production or in release mode that you need to enable this option. For Linux kernel, likewise, the build time increase was observed was less than 2 minutes, but it's about 4%. And the size of the build directory was very negligible. So it adds about 5 MB compared to a baseline build directory size of 1.7 gig. And the number of gitbom documents generated are about 60,000, 30,000 for each type, and they occupy a size of 1.6 gig. But it compresses well to about 600 meg. And the size of the VM Linux executable, the binary itself, increased only by about 64 bytes. So that is, again, very negligible and positive. So let's demonstrate an application of how to use this gitbom tree information for detecting CVEs in a binary, and this is work done by Warnicke. So the premise is gitbom tells us what constitutes an artifact, and From the GitBom tree, you can get a list of all the artifact IDs that go into building that artifact. And a CVE is associated with source files, which means you can get the artifact IDs or blob IDs from the repository, from the Git repository. So we generate a database mapping the CVEs to only the affected artifact IDs. And when we have the GitBom database as well as the CVE database for a software component, we can compare and run our search scripts to find which CVEs that we are tracking are open or fixed in that version. So this is the overall flow. So we start with the Git repository of, we've shown this for OpenSSL. We've start with the Git repository of OpenSSL, and we build the OpenSSL version of interest for which you want to learn about the vulnerabilities with the GitBom enabled LLVM toolchain, and generate a GitBom tree, and that is the GitBom database. In parallel, we also, it's a one-step effort to create a CVE database for OpenSSL, and then we can run the search scripts that uses the information from both this database and populate the result. So how do we create the CVE database? So the goal is to identify for every CVE only the artifact IDs that are impacted by that CVE. So what, it'll be more clear in the next slide, but what we propose is, usually it's easy to identify from the commit logs when a commit fixes a CVE, because the commit log says the CVE ID in the, so it can be easily inferred that this is the commit that fixes the CVE, but some manual effort needs to be done to identify which is the commit that introduced the CVE and find out the source files that are affected in that commit. So we've also initiated discussion with MITRE to see how such information can be captured as a practice in the commit logs, and also to add the Gitoid information to the CVE information as well. So this is just a proposal for a sample tag, like for every CVE, you identify the commit and say that this commit added the CVE and the source files involved in the CVE is, say, t1_lib.c. And similarly, another commit tag will tell you that the CVE was fixed here, and again, the source files affected, involved in the CVE is so-and-so. So with this information for every CVE, we can generate a database where for every CVE, we can say which is the commit that added it and which are the commits that fixed it, and we'll see why there are multiple commits that fixed it. So we have created an OpenSSL repository and tracking 7 high severity CVEs that are in OpenSSL. So this is a common scenario for the CVE commit. So let's say we have a commit A2 that introduced a CVE, and the commit A6 fixed the CVE. And let's say that foo.c is the file that's involved in this CVE. So any commit to foo.c prior to A2 is not said to contain the vulnerability. And any variation or any commit to foo.c, all the artifact IDs of foo.c in the repository after the commit point A6 is again not said to have the vulnerability because it is fixed. But between the commit points A2 to A6, whatever artifact IDs you have corresponding to foo.c is said to contain this vulnerability. Now, if you take a child branch similarly, B2 provides the fix. So any point after B2, the commits to foo.c after B2 is not said to contain the vulnerability. And from the starting point of the branch until B2, the vulnerability is said to exist. So this is the broad algorithm that we use to determine, to classify or to map the CVEs with the set of artifact IDs and use it in our search. So we've built OpenSSL, different versions of OpenSSL, and for the CVEs that we are tracking, we can easily, within a matter of seconds, just say that for version 3.0.0, this is the CVE that is open, this is the CVE that is fixed, and similarly for libSSL, what is the set of CVEs that are open and fixed. So we have a demo that will basically recap everything of what is being discussed.
We're at time.
Okay, all right. So I can just, okay, so this is basically an example of compiling a file main.c with dependencies main.h and add.h. So you can see that it's not playing. Okay. Okay, I don't know why I'm not able to go past. Okay, let me just conclude it. I'm so sorry. The demo is not playing. So to summarize, we have Clang and LLD prototypes available for llvm-gitbom, and we've shown an application for CVE detection. There is a Gitbom spec that is being written to standardize a lot of this information, and we're keeping pace with the prototyping to match the Gitbom spec. There are also, we found the need for several consumer applications that need more metadata beyond what is included, like what is the set of compilation options that are used, because different optimization levels will lead to different artifact IDs. So tracking that information, we want to identify a set of metadata and standardize them as well, so that all the tools generate a standard, have a way to standard representation of the data. And when the spec is finalized, we definitely want to take the time to upstream. And we have a wonderful Gitbom community with enthusiastic volunteers, and we welcome participation from the llvm-gitbom community as well. And you want to talk about the new name?
Yeah, so just very basically, the goal here is to actually cover everything. All the languages, all the artifacts, all the way up and down the stream, everywhere. We've talked here about ELF file embedding. Pretty much everything we've encountered has a place you can do what we've done with ELF file embedding. So if you are interested in enabling Gitbom support for other kinds of artifact types, like Mako would be beautiful, or other languages, because we have a lot of languages in the llvm community, or just generically getting involved. The net goal here is that what it takes to solve supply chain security for you and the other people you know who are dealing with this is set a frickin' environment variable when you do a production build. And you've got all the data that you need already generated and set aside to be able to have perfect fidelity for figuring these things out.
Thank you. Okay, any questions?
Okay. Thank you. CVEs don't work for the Linux kernel. There are too many vulnerabilities there. CVEs are created randomly for a small portion. Can we get this goodness for something that is not a CVE?
Yes. This can be used, CVE is just an example, but any class of any bug that you can just represent it in that manner and you want to track, it is possible.
One of the nice things about the way we approach this is that we only capture the structure of the tree, of artifact dependency tree, because we expect there to be other kinds of metadata that we've never even heard of that people want to represent by reference into the tree. And victory means that there are 10 times as many kinds of metadata that we've never heard of as the ones we have.
So we have all seen or perhaps written build scripts that derive things on the fly. A header out of an awk command, or God forbid, a curl command that pulls a couple megabytes off the internet randomly. You get what you deserve. How do you track that? I mean, in my environment, I essentially have, traditionally VMS has these listing files, and I capture every single line like a big -E that goes in the compiler. It's very manual, but I know the exact tokens that the compiler saw. How do you track that in the BOM?
Well, so we take a very agnostic view of this in the sense that there are always going to be build tools that generate things. So when you describe a command that generates source code for you, we think about that as being a code generation step, and it's just another build tool. We've had people talk about using essentially specialized comments to embed into the resulting file the embedded Gitbom ID.
Okay.
So that you can actually extend pretty much anything that takes inputs and spits out outputs to play nicely with this E.
So you let me fingerprint a dynamically generated something so you can track it. Because you
Exactly.
don't have the get ID to
Well,
pull from it.
when you generate the thing, it will come out as a file, and we can actually take the get object ID of that. You can compute get object IDs for things that don't exist in Git, and we do. So if your source code doesn't exist in Git, we will still generate output for you. If you
Okay.
generate a file that you never checked into a Git repo, we can
Okay.
still generate that output for you. And you can sort of track it down through
Okay.
things to the, I presume your awk is taking as input something that you do store.
And it may not be a file. I can be including from a mailbox or something like that, and I've done that too.
We can talk afterwards.
Yeah, I know, but
We have yet to find a level of perversity that we can't deal
Oh,
with.
I am perverse, let me tell you. I've done this for 40
I
years,
have a
I'm
great
perverse.
faith you're perverse.
But no, I think this is fine. There are edges that there's always some way to skirt around it.
But edges are where the fun part is.
Of course. It's where you get cut.
Okay, one last question, short one.
So I may have missed because I got in here about 5 minutes late, but how do you make sure that you get the fixed label on the right place?
Oh, so when you're talking about the fixed label in the right place, could you say a few more words there, context?
In your configuration management, you had A2, and A2 was the insertion point. How do you get the insertion point correct?
That's a manual step to go and figure out which commit.
Well, it is today. But part of the conversations that we're having with various folks across many languages and many organizations also involves some conversations with MITRE, because when you have some sort of metadata that says this is a vulnerability, and I understand we have people who have non-CVE cases, it is perfectly reasonable to allow people, just as you report, it's in this version, these versions of this thing with a package name, to also report just a list of known get object IDs for the files that it's sourced from. As you see more of these things fading into the ecosystem, the payoff from doing that becomes intense. And so I would expect the social oomph to move in that direction.
You know, like with OpenSSL, you might get, from the community, you might get, it's anywhere from version 3.0 to version 3.8, and not all the data may be correct.
Well,
I mean, how do you label that one point to say there is the
at
insertion
some point somebody committed something they thought fixed it, right?
Right. Well, that's the easy part. I'm saying where was the point where the defect
No,
was inserted?
I understand that. There's a certain amount that goes into the analysis of that. I agree.
Okay, I think we need to move on now. Sorry. So yeah, let's thanks to Bharathi and Ed for their presentation.